All right, the Christoffel symbol. One of the most fundamental symbols in tensor calculus. Why is it not called the Christoffel tensor? Any guesses? Because it's not a tensor. Okay, so the Christoffel symbol captures something very fundamental about the coordinate system and how it's defined in space. It captures the rate of change of the metric tensor, in a way. But the best way to define it in Euclidean spaces is through basis elements. It's through the elements of the covariant basis. So if we look at Zi, the covariant basis, a triplet of vectors. This is a tensor with vector elements. So it's 3 vectors. And of course, each one of them changes from one point in space to the next. So to capture that rate of change, which will tell you something very fundamental about how the coordinate system works, is the only thing you can do is take the derivative with respect to Zj, the coordinates. So lots of z's here. And you'll get 9 vectors. This is each of the vectors. We're going to do an example with polar coordinates. This is each of the vectors differentiated with respect to each of the variables. So in 3 dimensions, this would be 9 vectors. And each of these 9 vectors can be decomposed with respect to the covariant basis, giving us 27 coefficients, which of course are naturally organized into an object like this. Upper index k, I, j, zk. This is the definition of the Christoffel symbol. It's a symbol with 3 live indices. And this one, I'm sorry. It's today some of the most fundamental expressions I write down incorrectly. There you go. 1 upper and 2 lower. Start thinking about why this symbol is actually symmetric in its lower coefficients. So gamma kij actually equals gamma kji. That should be one of the things we talk about today. If you're following along very easily, just start thinking about why is it symmetric in its lower indices. Why is it that dzi, dzj is the same as dzj, dzi? In other words, when we talk about polar coordinates, why is it that der, d theta equals d e theta, der? I'm sorry. Der, d theta equals d theta, dr. So we'll see it. But what's the fundamental underlying reason? So there's one other thing I can say about this, which goes back to something we talked about maybe just about an hour ago, which is this is the component of this vector with respect to the covariant basis. So that immediately gives us an explicit expression for the Christoffel symbol, and it's zk dotted with dzi dcj. There you go. Of course, you could get this from this by dotting both sides with z upper m. Here you have a Christoffel delta, this will become m, then you'll rename it back to k, and voila, you'll have this expression. So maybe I'll box it like this, even though in deriving the actual values for the Christoffel symbol, we'll actually rely on this. So let's compute all the entries of the Christoffel symbol for the polar coordinate system. 2 dimensions, so 8 numbers. Yes?
Isn't the derivative of a vector 3 vectors?
Yes.
So that's
9, because it's derivative of each one of the 3 vectors.
oh, 3 to the
Yes. 3, go to 9, and then 3 coordinates, 27. Yes?
Why is it that the k isn't a dummy?
Because k isn't a dummy here. So it kind of this is one of those cases where you can go, where something dummy can become live. So usually contraction kind of means dot product and some information is lost, but when the contraction is with a vector, actually no information is lost in that contraction, and you can recover the whole symbol. But, so it is contracted here, but here it's live. Just like when we went from VI equals VI ZI, which is contracted, to VI equals CI dotted with V. Became live. It's the same sort of thing. Is that your question?
Yeah.
Yeah. So it just went to live. So here, in this expression, it's defined implicitly, but still uniquely, because when you say components of with respect to the basis, that immediately gives you three numbers. So this is an implicit but unequivocal definition for the Christoffel symbol. This is just its explicit expression. All right. Polar coordinates. Yellow chalk. Polar coordinates. Here's my axis. Here is the third one, just short of pi. Have to divide it into three pieces, like this, and like this. Pi, 2 pi, 3 pi, no, not pi.
Radian.
1 radian, 2 radians, 3, 4, 5, and 6 is almost 2 pi. There you go, that's my angle coordinate lines. Where's my unit? Somebody squatulate with our unit? No, my unit is safe. Here's our unit. So here's r equals 1. I've just had good luck in this course drawing polar coordinates, I have to admit. Okay, let's start. I guess this will be a good place to document it. Gamma 1, 1, 1, 1. Just take a moment. So they really come in pairs. So we'll first determine gamma 1, 1, 1, and gamma 2, 1, 1, because they're the same components. They're the components of the same two, I'm sorry. What am I trying to say? Yes, they're two different components of the same vector. Because it's the lower indices that determine the vector, and these are the two components of the same vector. And it's 1, so it's dz1, I'll use white chalk, dz1, that sounds not great, but it's basically E sub r, which is the unit vector, E1, or we should now denote it by Z1, everybody remembers this, that's what a Z1 looks like? It's E sub r. So in the polar notation, it's E sub r. It's the unit vector that points in the radial direction. And now the question is, if I go from a point and I change r a little bit, because it's DER, so the vector we're evaluating now is DER, dr. DZ1, DZ1. That's why it's gamma 1, 1, and we want its two components. But now let's just figure out what this vector is geometrically. What is the rate of change of this vector as you move radially away from the origin? 0. This equals 0 vector. I know how to decompose that. 0. Great. 2 out of the 8 are taken care of. Next. Gamma, I guess we'll go for gamma 1, 2. Gamma 1, 2. 1 and 2. So what does 1, 2 mean? It means DER d theta. That's the vector we have to consider. DER d theta. And once we figure out what this vector is, decompose it with respect to the covariant basis. So describe to me in words what DER d theta is. That's right. So all E sub r does is rotate with quote-unquote unit angular velocity, and it's the unit vector. So it's basically just does this, even if it's not always at the origin. If we were to bring it to one and the same point, it just does this with quote-unquote unit speed. So we've worked with this sort of change before. Is it working? Okay. And we know that what it is just a vector in the orthogonal direction that also equals 1. So this, let me draw it everywhere. So this is, at each of the point I've drawn dE sub r d theta, always the unit vector. This one I overshot a little. It's the unit vector that points in the orthogonal direction. Great. Now decompose this vector with respect to the basis itself. For that you have to remember what E sub r looks like, which we already do, and what E sub theta looks like. Do you remember what E sub theta looks like? Yeah, it's orthogonal and its length is r. So because it's orthogonal to this one, I'm guessing this is 0. This is the interesting one. So what is this one? 1 over r. That's right. The vector, the basis vector itself, E sub theta, is length r, and you have to decompose a vector of length 1. So it's 1 over r. There you go. Now let's switch to gamma 2, 1. Gamma 2, 1. Gamma 2, 1. 1 and 2. Okay? That's dE theta dr. That's going to be an interesting one. So I might as well erase, we're done with this one. dE theta dr. So let me draw E sub theta. That's the one we're working with right now. dE sub theta dr. So it equals its unit here. It's twice as long here. Then if you keep going 1 or more, it would be 3 times as long. So E sub theta very much depends on r. So what is its rate of change with r? dE theta dr. I'll let you think about that for a moment. And which direction does it point? Well, you just have to do that finite difference and then think about what happens to the difference as delta r goes to 0. What's the difference between this vector and this vector? R. And which way does it point? Its length, wait, that's right. That way. It's something like this minus something like this.
The difference, yeah.
The difference points this way. And you also have to divide it by delta r. So what length what length? 1. Right, and if it was somewhere in between, it would be like this, right, and it would be like this. So the rate of so it's constant rate of change. So the vector grows linearly because it's a unit vector times r. So when you take the derivative with respect to r, it just becomes the unit vector in that direction. Hey, it's the same vector as dr, der, d theta. So this and this are the same, which is what I promised. in this context, it kind of almost seems surprising because the way you arrive at this unit vector is totally different in both cases. In one case, it's something that rotates and therefore becomes length 1 in that direction. In this case, it's something that constantly points in that direction but changes its length. Kind of nice, but it's the same. This is 0 and this is 1 over r. So as promised, they are the same. Okay, gamma 2, 2, 2. Gamma 2, 2. And gamma 2, 2. So 1 and 2. Can you guys try and think it through on your own? Think about what happens to this vector as it, right, e sub theta, these are what e sub thetas are, but now we're thinking about what happens when it rotates. What happens to this vector as a function of theta? Well, here's how to think about it. It's once again something that just rotates rather than starting in this direction and now starts at the 90-degree angle and just rotates with unit angular velocity, so to speak. And its length, and instead of being length 1, at each point it's actually length r. So around here it'll be something of length 1 rotating, but here it will be something of length 2 rotating with unit angular velocity. So you know what happens in these situations. It becomes a vector that's orthogonal to the vector itself. It's just that this way, now it'll point this way. And its length will be r. So now you have to decompose something that's radially inward and has the length r. So what components does that vector have with respect to the local covariant basis?
Negative. 1 over.
Negative, think about it. So this is E sub r. E sub r is unit length. And you have to decompose something that's length r. Say it. I'm sorry?
Minus r.
Minus r. So this one is minus r, and there's no theta component, so it's 0. So out of the 8, there are only 3 non-zero ones out of the 8. And the rest are 0, which is typical with nice symmetric coordinate systems. So that's the Christoffel symbol. It's something basically as fundamental as the metric tensor. The metric tensor captures or the covariant basis. The covariant basis captures the rate of change of the position vector with respect to coordinates. And this is kind of like the second derivative. This captures the change in that rate of change. So it's very important. And it's kind of surprising that you don't really need to go to third order derivatives. Actually, you have to in the Riemann-Christoffel tensor. Yes?
Can you raise and lower indices on the Christoffel?
Of course.
You can juggle indices?
Yes. So let me just write it right now. And then there's the question, the important question that I didn't address. Which index is first and which one is the second? And there are different conventions. So we'll use the same convention as Weil in his book. The upper index is first. So this was, you can say, the definition of the Christoffel symbol with an upper index. Dot dzi, dzj. Then we lower the indices on both sides. It becomes gamma, k, I, comma, j. So I put a comma just to remind myself that that's my convention, that this special index is first, and the other two are second and third. So a comma here is not necessary as long as you remember, but I just like reminding myself with a comma. Well, you just have to dot it with a covariant index. Dot dzi, dzj. There you go. Lowered index on the Christoffel metric. Excuse me, on the Christoffel symbol. Then there is another super fantastic question. If I were to differentiate the contravariant basis, if I were to differentiate the contravariant basis and get 27 new vectors that way and decompose them once again with respect to the contravariant basis and the 27 numbers that I get, will it be somehow related to the Christoffel symbol to begin with? It'll be different, more or less, different 27 numbers. Yes?
Is that dk a vector?
Yes. Thank you. So how would those 27 numbers be related to these 27 numbers? It's a fantastic question, but I think we've right now spent enough time with the Christoffel symbol, and I'm eager to start using it. So let's pause here and talk about the covariant derivative.